This video involves what is typically the very first application of a definite integral, and that is the area between curves. Alright, typically what we have is you'll have functions f of x and g of x are continuous. And f of a equals g of a, f of b equals g of b, but f of x is greater than or equal to g of x for all x that are between a and b. So it wouldn't matter if I put less than or equal to for that. It really doesn't matter at all. Everything's continuous, so don't worry about jumps or anything like that occurring. Anyways, what I have then is a picture that looks like this. Just a rough sketch, nothing special. Let's say I start with A, there's B, and then F, who knows, just some sort of function comes through. There's f of x. And then we have that f of a equals g of a, so let me kind of make that happen here. And we'll say this is g of x. So we have f of a equals g of a, and f of b equals g of b. I want the area between them. So I'm looking for the area in here. So you'll remember from Calc 1 that if I have a continuous function defined on an interval from a to b, just to make this work, I'm going to make my function be the same one that I'm talking about above. So this will be f of x. Now if you go between a and b under the curve but above the x-axis, the area inside of here is well known to be the integral from a to b f of x dx. Well, in the same vein, let me go ahead and grab g of x and do hopefully as much the same kind of a thing for g of x that I did for f of x. Let me get an idea of what was g of x. Kind of went like that. So I'll go ahead and put a in the same spot, b in the same spot, grab that function again, and let me see, that was 1, 2, 3, about 4. 1, 2, 3, 4. So, well, can't quite. Something like this. So we know the area in here is the integral from a to b g of x dx. So when I take the integral of f and I look at the integral of g, if I want the area contained between them, let me go ahead and smash these two things together and show you what I'm talking about. Well, I did draw a picture of what I wanted, but there's a, b. Let's start with f of x again. What I'm going to do with it, the integral here, the area that will be, let's call this a1 I'm going to need to keep track of these things. So we know A1 equals the integral from A to B f of x dx. Now then g of x comes through here. I know it's not exactly the same as before, but there's g, and it's got its own area, and its area down here is given by a sub 2, I'm going to call it. But I'm also going to double hatch so you can see what the overlap is. Okay? Then if I look at this area, the area under the whole thing here, and I subtract off this double hatched area, I will get exactly what I'm looking for. So the area between the curves is a1 minus a2, which is the integral from a to b f of x dx, minus the integral from a to b g of x dx. And you know, based on the property of integrals, that you can combine this into one integral and this is our formula. Let's just call it A. That's the area between the curves that I'm looking for. Note that F is what the books always call the upper function on the interval from A to B. So it just means that f is greater than or equal to g for the entire interval. So another thing, a lot of times students will forget which one is the upper function and which one's the lower function, or they'll do something like they'll just swap them, or they'll ignore it, whatever. You must remember this. This is a big note. Area can never be negative. The reason I mention that is because if you do get it backwards, which one is on top and which one is on the bottom, say you subtract in the wrong order, you'll get a negative answer for certain. And you will know that something went wrong. One of the things you can do, if you don't want to, I don't know how to put it, bother yourself, with upper and lower functions, you can simply do this. The area here, just do this. Put the absolute value around it. And then it won't matter which one is the upper function and which one is the lower function. You'll get a positive answer, assuming all the other work was done correctly. And there you go. So this probably this is the better one. If I had to pick one of the two, this would be the one that I'd want, because like I said, this works for anything. Notice that the functions are continuous, so there's no breaks. They are containing a region. That's the part where they have to be equal at the endpoints. So they have to have something in between them. Let's do some examples to show how these calculations work. This shouldn't be that big of a deal. Hopefully this section is simple and a nice way to start off the semester. Believe me, the complications get difficult quickly. So this is a nice, comfortable section to begin with. Anyways, first example up next. Let's find compute. That's better. Compute the area bounded by the curves f of x equals 10 minus x squared and g of x equals x squared plus 3x plus 1. Now the term bounded means the area is not going to be infinite. The first thing I would suggest doing here is to graph both the functions together and see what we're dealing with. These are both quadratic or second degree polynomials. They're parabolas, they're easy to graph, but to make life a little bit easier, I'll typically run over down to the calculator. Let's turn this thing on. You can see that I've already done the problem in advance, but I'm going to redo it so that you can see all the steps. So let me clear everything from the calculator's y values. So you know the drill. Go into the y, press the y equals button. In y1, let's put 10 minus x squared. If you hit enter, it'll take you down to y2. And in y2, put x squared plus 3x plus 1. And to get my first graph, I almost always click zoom and then the number 6. It's what they call the standard viewing rectangle. It stretches from -10 to 10 in both the x and y directions. So here we've got ourselves a graph. Let me get a picture of that thing. Alright, we got our graph. Let me go ahead and label the various parts. This graph right here, the first one to be drawn, was the 10 minus x squared. So that is f of x is that one. And then this one that goes like this from here to here, that is g of x. So the function that is on top here is f of x, and the function that's on the bottom here is g of x. So to calculate this then, the area that I want is in here. So the area is going to be the integral from a to b, and it will be f of x. So f of x, where are you at? Is 10 minus x squared. And then g of x is x squared plus 3x plus 1. Notice that I put parentheses around g just to be on the safe side. Now the only thing left to do then is to figure out the a and b. I need to figure out the places where these two functions intersect. So I need this spot here, right there. I need that. That's the beginning of the interval. And then I need that one over there, which is the end of the interval. So down under here, that'll be A, and down under here, that'll be B. How do you find out where two functions intersect? Well, you set them equal. So, set them equal to each other. 10 minus x squared equals x squared plus 3x plus 1, and then solve for x. So I am going to take everything to the right hand side of the equal sign. 0 equals 2x squared plus 3x minus 9. And in the hopes that this factors, I will set 0 equal to, and I will set up my two factors as they probably should if they're going to factor. I'll have a 2x, and then I'll just have an x, and then the rest is just trying to figure out these numbers left. And you've most likely played this game a million times. Here, you need whatever goes in this spot and whatever that goes in this spot has to multiply together to give you -9. Your options are going to be either 1 and 9 or 3 and 3. So since I have to have a negative, I'm going to have a 3 and a -3, or I'll have a 1 -9 or -1 9. I see just right off the top that 1 and 9 have no shot, but 3 and -3 have a shot, because if I put a +3 here, then the 2x times that 3 will give me 6x, and that allows me to put a -3 here, and so the 6x minus the 3x will give me a +3x, and then of course I get -9. So when I set each of the factors equal to 0, I get x equals 3/2 and -3. So this one here, the a, that equals -3. It certainly looks like it from the graph. And the b equals 3/2. So let's go ahead and put my area again. So the upper function was the 10 minus x squared again. 10 minus x squared minus x squared plus 3x plus 1 dx. And with anything else, simplify inside the integral before you do anything else. So I'm going to have -3 to 3/2. This probably wasn't escaped on you. You're going to get the negative of that particular expression here. So that's going to equal 9 minus 3x minus 2x squared dx. And then the rest of this is something, this is a particularly simple integral to do. 9x minus 3/2 x squared minus 2/3 x cubed from -3 to 3/2. And then plug these numbers in. I'll have 9 times 3/2 minus 3/2 times 3/2 squared minus 2/3 times 3/2 cubed minus, and now let me put these, but throwing in the -3. So I'll have 9 times -3 minus 3/2 times -3 squared minus 2/3 times -3 cubed. One of the things with integrals, we tend to try to do too much in our heads. I say take your time. Notice that I put the minus and I put parentheses in here. A lot of students will actually try to do this stuff in their head. You're always going to get some negative wrong. Just please don't do it. It is not going to yield a positive result almost ever. So I'm just going to go across and do these. Just take your time, embrace the problem, I guess. Relax through it. So I have 9 times 3/2. That'll give me 27/2. Then this is like 3/2 to the third. So I'm going to get -27/8. Then you can save yourself a little time. Like when I do this, the 2/3 and the 3/2 cancel. So like when I do it, I can make this into a 2. Just little things to help us out. So this will be 9/4. And now the minus. I'll take care of the minus in front of that in one of the later steps. 9 times -3 gives us -27. -3 if I square it is 9. And 9 times 3/2, that'll be 27/2. So I get -27/2. Remember, the negative will stay here. But this will all become a positive. And if you look, I can do a little bitty bit of canceling. I'll make this a plus, a plus. I can take one of these out. All these little notes help me. 2 times 9 will be positive 18. Alright, here I'm going to get the common denominator of 8. So I've got 4 times 27 is 108, 108 over 8. That's already over 8, 27 over 8, and minus 18 over 8. Minus, I'll simplify it here a little bit. I'm going to do the negative 27 plus 18. That will give me negative 9. I still got the negative 27 over 2. So what I'm going to do with this then is change that 9 into an 18 over 2. Okay, let me simplify a little more. 108 minus 27 is 81. 81 minus 18 is 63, so I'm going to have 63 over 8 minus, and now inside of here, I'm going to have negative 45 over 2. I'll do the same thing as before. I'm going to get this over 8, double negatives cancel, and I'll have 63 over 8 plus 180 over 8. And that equals 243 over 8. Or if you are one of those decimal fanatics, this is 30.375 exactly. Now, before I walk away from this problem, you should know that you can check this answer on your calculator fairly easily. As long as you knew where they intersected, and you can do that all with the calculator. Let me show you how it works. Let me come back here. Let me turn it back on, and here's our graphs. If I want to find out where they intersected without doing pencil and paper, you can click over, press second, and trace. That will activate the calculus screen. You can go here and find intersect. That's number 5. So choose number 5 for the intersect. Now you got to get it close to the ones you want. So I'm going to start over to the left, and it will say the first curve, which that's y1 there. So we say enter, and then the second curve, that's y2, enter, and then it wants to give you a guess. So put it close to the point of intersection so that it doesn't confuse it with the other intersection point. And you'll see this will give us a negative 3. You can see the x value is negative 3. Repeat the process to make sure that you can get the 3 halves for the other intersection point. Now the reason why I bring this up is I can check this answer, this 243 over 8, by going back to y1, or y equals. Going back down, go to y3, and then do this. Click your vars button, go over to y vars, hit enter so that you choose option 1 for function, and then hit enter again so that you choose y1. You see in y3 it has so far entered y1. I'll press a minus. I'll hit vars, y vars, enter. Now I'll scroll down here to y2, enter. See what it did here? y1 minus y2. In fact, I can do more. I can go up to the other graphs and I hit enter. I put the cursor over the equal sign and I hit enter. It deactivates the graph. And I can do the same for y1. Enter. So that I'm only interested in graphing y3, which is the difference of the two functions. So I already did zoom 6 before. Let me go ahead and select graph. Now when you're doing it, you're unconcerned with this particular graph, the difference of the two curves. You couldn't care less about. However, you can use this to find the answer by finding the area under this curve from negative 3 to 3 halves. It just so happens to be the exact places where this thing crosses the x-axis. Here's how you do it. Press second. Press that trace button again to get to the calculus menu. Choose option 7, the integral. What it will ask you for is a lower limit. You may type in negative -3. Hit enter. For the upper limit, you may type in 3/2. Enter. And you'll see that it puts a shading underneath the curve to let you know what it has found. And look at the answer, 30.375, which if I look back to our answer, that's exactly what we got. So you can use your calculator to help you solve these. Even if you're required to give an exact answer, you can use your calculator to help you verify that answer. Compute the area bounded by y equals 1 plus radical x and y equals 1 plus 1/3 x. So as before, I'm going to graph these things, get an idea of what I'm dealing with, unless you know. I mean, honestly, this is not the biggest thing in the world. You know what the square root of x looks like, you shift it up 1 unit. You probably know what 1/3 x looks like, you shift it up 1 unit. So, anyways, let me go ahead, back to the graph. Y equals, I'll clear out my y1, 1 plus second square root of x, hit enter. Let me clear this thing out. 1 plus, I think the easiest thing to put in here would be x over 3. And then I'm going to leave y3 in there, but I'm just going to deactivate it right now. And let's go ahead and graph the two of these. Well, you can see it's a small sliver of area here. I think what I'm going to do is change my window a little bit, and maybe I can see that if I go from -2, I think 10, I still need to go to 10, but for the y values I may say -1, let me say 5 and see what happens. Let me regraph this. So there's the square root one, and there's the other one. Interesting, they don't intersect here, and the square root one stops at 0, doesn't it? Of course it does. They would intersect if there was a spot there. But let me go ahead and grab this picture and throw it into the notes and work on this thing. Alright, so the area that I want is in here. I can see that the square root function is on top. So 1 plus radical x is in the numerator, at the upper function. The lower function is the 1 plus x over 3. Alright, let me find this intersection point, although I think it might be 1, 2, 3, 4, 5, 6, 7, 8, 9. It may be 9, but I'll calculate just to be on the safe side. Interesting there. Look at that. That's not an intersection point. Let's set these equal to each other and see what happens. This is going to be not so bad to do. So I'm going to set 1 plus radical x equal to 1 plus x over 3. And of course subtract 1, so I get radical x equals x over 3. Now you're probably taught to square both sides, or let me multiply by 3 first. 3 radical x equals x. Square both sides, I get 9x equals x squared. I'll subtract 9x from both sides. And then I will factor this. So what are my answers here? X equals 0 and x equals 9. So I was wrong about them not intersecting. It actually does intersect here. It's just that the curve, it's so strongly curved that it's hard to see. You should know by now, if you've dealt with this calculator for very long, it has some very limited graphing capabilities. So it just cannot graph this curve. It's too blocky. But it actually does curve down there and touch at 0. So 0 and 9 are my limits of integration. So the area is going to be the integral from 0 to 9, and I will take the upper function, which was the 1 plus radical x, subtract the lower function, which is the 1 plus x over 3. Of course, the ones will cancel out just like they did in the equation. So I get the integral from 0 to 9, square root of x minus x over 3 dx. The radical symbol is not one that I enjoy very much. If I were you, I would change this thing to x to the 1/2. That means when you do the integration, you're going to get x to the 3/2 over 3/2, or 2/3 x to the 3/2. Over here, this will be x to the first power. So you're going to have x squared over 2. It'll end up being 1/6 x squared, and that is going from 0 to 9. I always like when there is a 0 here, because I don't even have to do that part in the integral. All I got to do is throw the 9 in here. So I'm going to get 2/3 times 9 to the 3/2 minus 1/6 times 9 squared. Let's see, 9 to the 3/2. I like to do the square root part first, or the half. 9 to the 1/2 is 3, but 3 to the third is 27. You know what else I saw? You could have done some canceling here. I'll do that later, but I just thought I saw that right off the bat. So I have minus 1/6 times 81. So let's do my canceling. Go get rid of that. And then this, I can take that and change it to a 27, change that to a 2. So I have 18 minus 27/2. 18 is, of course, 36/2. So I get 36/2 minus 27/2 is 9/2, or 4.5. So, go to the calculator, see what happens. Now, I'm going to go back to my y equals, and I'm going to deactivate the first two curves and activate now the third one and find the integral of it. We found out the intersection spots were 0 and 9. So let's first graph. You have to graph it first before you can use the option, the calc option. So second, number 7 is what I want, the integral. The lower limit, I'll put in 0. Just puts a little star there to let you know. And then the upper limit is 9. So all this stuff can help you verify that what you're doing must be right. There it goes, 4.5. Yes, it has a little bit of an error here, but that's okay. This tells me with no uncertainty that I have the right answer exactly. For the last example, it may seem like the rug is being pulled out of you here, but it's just because we want to have a handle on more complicated regions than what we've been doing previously. So, compute the area contained between the graphs of x equals y plus 1 and x equals y squared over 2 minus 3. So what's happened now is they've switched it to being x is a function of y instead of vice versa. You can't, oops, I made a mistake here. You can't necessarily just ignore this order or try to solve for y in terms of x, because you get a plus and minus here. It's not completely invertible. There are ways around it, things of that nature. But I'm going to approach this in the way that most calculus books do, and leave it like this and graph it. And your graphs are sideways. Let's start with x equals y plus 1. You can easily solve for y and get y equals x minus 1, but let me just show you some of the thinking I have. Instead of solving for y, like you always need to, because down here I'm not going to solve for y down here. It'd be unpleasant to do it, but let me show you what I'm talking about. X equals y plus 1. We still have x and you still have y. Treat this as it's a line, a linear function, and you can see that when y equals negative 1, x is equal to 0. So when y equals negative 1, x equals 0. And then you can also like set x equal to something, but I would once again just pick another value for y. Say y equals 1. When y equals 1, x is equal to 2. And then it being a line, you can just connect the two of them. Got it. So that is x equals y plus 1. And now this one here, x equals y squared. We have this one here. I'm going to graph it. X equals y squared is nothing more than a parabola that has been flipped about the line y equals x. So this is x equals y squared. Well, y squared over 2, as you may imagine, is simply going to take this graph and make it shorter. It will have the effect of doing something like that. And then the minus 3, if this were a regular function, you would shift down 3, but in fact we have to shift lower 3. So that means I'm going to shift to the left 3 units. And all the way at negative 3, I will have something here like this. I really don't care where it intersects the y-axis. When I put these two together, I care where it intersects this line. So now let me put these two together on one graph. Unless you solve for y, your calculator is not going to be able to do this stuff. Some calculators, some of the better TI calculators right now, will allow you to graph things without having to solve for y explicitly. They call it graphing a relation. And a lot of things can do that nowadays, just not Texas Instruments 84, I believe. I know the calculator that I use on this screen can't do it. So, let me put them together myself. I had the one went like this. I really don't care where it crosses anything. The other one was a parabola that came at negative 3 and went something like this. And went something like this. So since I'm talking about x in terms of y, I'm actually going to find the intersection points in terms of y, and I'm going to integrate in terms of y. So I want these intersection points. And the area in between, or the area contained between the curves, is here. And this is not exactly like it was before. Your upper and lower might be a little more complicated to you, but it shouldn't be. You should know that the x-axis is nothing more than a number line. The bigger numbers go to the right, the smaller numbers go to the left. So with that in mind, the upper must be to the right, and the lower must be to the left. Of course, if you throw absolute values around the whole thing, it won't matter anyways. Let's find the intersection, at least the y values of the intersection points. At x equals y plus 1, and then I had x equals y squared over 2 minus 3. I'll set them equal to each other. Y plus 1 equals y squared over 2 minus 3. I'll take everything. I think what I'm going to do first is multiply everything by 2. And now I'll take everything to the right hand side. And factor. And I get y equals, oops. Y equals -2 and 4. So the area then is going to be the integral from -2 to 4. The upper function was y plus 1. The lower function was y squared over 2 minus 3. I made a common mistake. Since I'm talking about y, the integration is in terms of y, and I will leave it to the student to verify that this equals 18. Now if you want to do it on your calculator, to be honest, all you got to do is swap x and y. You'll get the same answer because geometric region, the area of that region is unchanged if it's reflected about the line y equals x. Also, one last thing that could happen to you sometimes is just one last note that I'll make. And you could have functions that do something like this. I could have, say, one function, say that's f, but then I could have another function, g, and they could have all sorts of pockets of area between them. Well, what you have to do in each of those then, one more, A, B, C, D, oh, E is not a good one to use. Well, I can use letter. Let's use an E, not to be confused with the exponential E. So what you could do is you could calculate this piece here. Here g is the lower function and f is the upper function. So for this piece, you could do the integral from a to b, and then you could do f of x minus g of x dx. And then for this piece here, you would have the integral from b to c. You would then do g of x minus f of x dx. And then you could do this one here would go from c to d and this one from d to e. What you could do then is add them all together to get the total area. If you tried to do it just as one thing, then sometimes the g would be canceling f. They would be in the wrong order, so your answers would get all messed up. The positives and negatives, you wouldn't even be able to fix it in a million years because you have all these untanglings you have to do. So just keep that in mind. You might have to break it into several pieces. And with that in mind, I don't think there's a lot more complications for this particular section. So I think that example, we'll leave it at that and call it a day on this particular section.